Is all clear? Good. It's all clear? Nobody is facing any issue there? Actually, last time I shared the pic of that QR code. Were you able to open through that, scanning it by any other mobile? Were you able to do it? I think there is some issue with direct link sharing, but were you able to, kind of, when we shared the pic of that QR code, were you able to scan it? You were. Okay, fine then, no issues. Fine, I think then it's better I'll send it like that only. A link is not working, I can understand, I could see that it was not opening. You can scan the QR, no, so fine, that is okay. Same that way only I'll do not worry about it. Okay. Now, I think where did we finish off in the last class? I think bond energy concept was done, if I'm not wrong. Bond energy concept we have finished. Bond energy concept, I think we have done there. See, whoever has newly joined and what are all those things, so you can contact the, kind of those who are the admin persons, they can, kind of add you there. Okay, bond energy done, fine. So now let us start off this session with one particular question here. I'm writing down the question, you have to calculate it, okay? So the thing is, calculate change in enthalpy for freezing of 1 mole of H2O liquid at 10 degrees Celsius to ice at minus 10 degrees Celsius, given delta H fusion is 6 kilojoule per mole and you are having Cp for H2OL, which is 70 joule per mole Kelvin. You are having Cp for H2O solid, which is 30 joule per mole Kelvin. Right? So the thing is, this is a given question. You have to calculate the enthalpy change for freezing 1 mole of H2O liquid, which is present at 10 degrees Celsius, and you have to make the ice at basically minus 10 degrees Celsius. So if I go for looking at the entire process, so we are having H2O liquid, which is present at 10 degrees Celsius. So first you are going to cool down the temperature of this liquid, bring it down to 0 degrees Celsius, because phase change always happens at a particular temperature. Temperature will remain same there. So whatever is the enthalpy change here, let us say I am denoting it by delta H1. And the thing is then I'm going to do the phase change here, which is H2O solid at same temperature. Let us say this is delta H2 and I'm writing this as a phase change. Now I'll be lowering the temperature of this ice and making this to minus 10 degrees Celsius, and this is basically delta H3. So I want to know the change of this entire process, starting from this, ending at that. That means delta H is going to be summation of delta H1 plus delta H2 plus delta H3. I'm not going to solve this entire question. I'm simply giving you a little bit of hints here. Now tell me delta H1, temperature is changing. Which formula I'll be applying here? Voice is resounding. For others also, is it the same? Sai has written voice is resounding. Is it the same for other persons also? Because if it is only for you, then maybe fault from that side, Uta. No, that means it's absolutely fine. Okay, fine. Now the thing is, here what you are having, you are lowering down the temperature. Which formula will be utilized here? Acha, Tejaswini is writing ms delta theta. Now the thing is, I have given you Cp value. So here you won't be applying ms delta theta, you will be applying Ncp delta T, right? Now, so here it will be Ncp. Cp of whom? H2O liquid or H2O solid? Whose Cp I should take? Sometimes so it's okay, beta. Need not worry. My voice is also fantastic there. So will I be writing this one for H2OL? Tell me about delta T. Number of moles is 1. You are having Cp as 70. What about delta T? What is the value of delta T? Yes, good. Sham and Fatima, they have replied. What about delta T? Value of delta T here. 10 or minus 10? See, you people have to take final minus initial temperature, na? So it will become minus 700, minus 10. Do not take only the magnitude. Many of you have taken 10, 10, 10. Hai na? Srushti has taken it correctly. Good. So the thing is, you should be very clear that temperature change is final minus initial. Got it? Okay. Now next one is delta H2. Now tell me, what is fusion? Solid to liquid or liquid to solid? What is fusion? Solid to liquid or liquid to solid? Sham, fusion beta, fusion. Melting. Solid to liquid. Few intelligent creatures are here, hai na, who are saying liquid to solid. Are you wonderful species? You don't have any right to exist on this planet. Hai na? Melting also we are doing it reverse, right? So here you are having solid to liquid as fusion, which is melting. Now are we going in that direction or else opposite to that? We are doing liquid to solid. So that means, can I write down this is minus delta H of fusion? So I'll be writing this as minus 6 kilojoule per mole. Now here be careful with the unit, because Cp is given in joule, delta H is given in kilojoule, right? So the thing is, here you will be writing minus 6000 joule per mole. Unit consistency should be maintained. Now in the third process, delta H3. Delta H will be what? Ncp. And in fact, let me write down to some other side because it is becoming clumsy here. So delta H3 is Ncp, Cp this time of H2O solid, and delta T. So 1 mole and this is 30. Tell me delta T this time, all of you. What is the delta T? Yes, you have replied correct also. Good. Tell me, what is the delta T in the last case? Again, 10 or minus 10. Final is minus 10, initial is 0. So it is going to be minus 10 here. So minus 300 joule per mole. Now simply we are going to write down delta H as delta H1 plus delta H2 plus delta H3. So you are having here minus 700, minus 6000, minus 300. So ultimately minus 7000 joule per mole, or else minus 7 kilojoule per mole. I hope it is clear to everyone. People are correcting when I am pointing it out, not before that. So be careful here with the unit as well as the delta T here. And once you are done writing, let me know. Done? And this is one of your NCERT exercise problem itself. Only thing is little bit data here and there, but concept remains the same. Okay. Now let us go for third term here, which is resonance energy. After bond energy concept, one more term, which is resonance energy here. When I talk about resonance energy here, I'm referring to the compounds where this resonance phenomena is possible, right? And what is resonance? It is basically delocalization of the pi electrons, right? Or else delocalization of the electrons. And do you agree that whatever is the compound, or else if a compound is having delocalized electron and there is another compound which is having localized electron, so that compound will be more stable where resonance phenomena is there, right? So I'll say that resonance brings the stability in any given compound. Now let us try to understand what is the definition for this resonance energy. Now the simplest molecule which I'm taking here is, let us say, benzene. This is one of the resonating structure of benzene, and the another resonating structure here is like this. These two are resonating structure, and you are having here hybrid of it, right, which is resonance hybrid. Now, can these two resonating structures flip among each other? Can these two resonating structures flip among each other? Sometimes first structure, sometimes second structure. Is it possible? Is it possible? Equivalent resonating structure, I know. Only one person has till now, I think, Smriti, Sai. Yes, absolutely correct. Hai na? So the thing is, they are hypothetical. There are mind's creation, right? Actual structure which exists is resonance hybrid, no. So if something is basically hypothetical, how it can flip among each other, right? So now the thing is, these are hypothetical creation. Now let us come back to the resonance energy here. I'm drawing energy level diagram here. Now resonance hybrid is more stable, so I'm showing lower energy, and you are having basically here resonating structures. Since they are like equivalent, so they are having the same energy. Now the thing is, whatever is the energy difference between the resonance hybrid and the most stable resonating structure of any given species, that is known as basically resonance energy, right? Here to both of them they are equivalent, but if at all I take 1,3-butadiene, you know that basically you can always draw a resonating structure like this. This is plus here, minus here. So out of first and second, first is more stable and this resonance hybrid will be looking like this. So at that time, if at all I have to define resonance energy, I'll say that energy difference between this resonance hybrid and this resonating structure, because it is more stable among these two, right? So hopefully it is clear. So let us write down the definition. I'm writing down the definition beside all this. So you please copy down this diagram. So I'll write down the energy difference between resonance hybrid and the most stable resonating structure of a given species is called as resonance energy. Write this down, and once you are done, you can thumbs up so that we can go further. Finished? Now I'm going to write down the formulas for calculating resonance energy. So first formula is enthalpy of formation experimental minus the enthalpy of formation calculated. Calculated means this one will be generally based on bond energy data. Similarly, you can have enthalpy of combustion data. So in that case, calculated minus enthalpy of combustion, experimental. Similarly, you can also have enthalpy of hydrogenation data. So that is also calculated minus enthalpy of hydrogenation, experimental. So just write down this as a formula, then we'll basically try to understand the application of them. So here examiner will be providing the enthalpy of formation or combustion or hydrogenation of any compound. In that case, in any given question, then please treat that as the experimental value, because examiner never wants you to do the experiment and get the value there when you are calculating. And when I say calculated value means theoretically you have to calculate on paper using some of the supporting data which will be given by the examiner, right? So first write this down, and remember only for enthalpy of formation you are having experimental minus calculated, rest place you are having calculated minus experimental. Write down the formula and let me know. Then we will try to understand resonance energy concept based upon the enthalpy of hydrogenation here, or the concept of hydrogenation. Let us say I am having cyclohexene, right? And in cyclohexene, we have one pi bond. So basically, for its hydrogenation, I require 1 mole of hydrogen, and you will be getting basically cyclohexane here. And the thing is, delta H hydrogenation for cyclohexene, there is a standard data which is minus 120 kilojoule per mole. That means when cyclohexene undergoes hydrogenation, 120 kilojoule of heat is liberated, right? Now, similarly, if I take a hypothetical compound and I'm calling it as hypothetical, I'm not calling this as benzene, because I'm assuming that in this particular compound, these pi bonds, they are not moving anywhere. They are not delocalized, they are localized. Okay, we are assuming, right? So I am giving new name to this. This is cyclohexa triene, and here I am saying this is hypothetical. Reason being, I am assuming that the pi electrons are localized. They are not moving here and there, right? Or they are not getting delocalized. So for 3 pi bonds, you require moles of H2 so that it gets converted into cyclohexane, and you will be having enthalpy of hydrogenation here as what? 3 into this value minus 120, you will be minus 360 kilojoule per mole, right? Able to understand so far? Now when scientists took actual benzene, right? I am writing here benzene, and I am saying this is actual. Actual reason being, here pi electrons were actually delocalized. They are not present at the same place. When they carried hydrogenation of benzene, what they identified that cyclohexane it is forming, but the enthalpy of hydrogenation is at minus 208 kilojoule per mole. Now what you need to understand here is, they didn't know about, like, some stabilizing effect is there in benzene or not. So ideally, if there is 3 pi bond in benzene, right? According to, when they are comparing with the cyclohexene, so cyclohexene is having 1 pi bond. So for its hydrogen, 120 kilojoule of heat is getting liberated. So here also basically for 3 pi bond, ideally you should liberate 60. But in reality, what was found when they experimented? What they found that it is liberating 208 kilojoule amount of energy. That means, do you know one fact, that whichever compound is more stable on hydrogenation, it releases less amount of energy, right? So it implies that ideally benzene should have released 360, but now how much it is releasing? Lesser than what is expected, which is 208. Lesser than expected means what? It is already having some stabilizing effect inside it, and that is because of the delocalization of the electrons. And so from there, that kind of concept of resonance or resonance energy came up. So now if at all I have to find the resonance energy here, so I'll be writing resonance energy as what? Delta H hydrogenation, which is calculated, minus the delta H hydrogenation, which is experimental. Now I'll be treating this minus 208 as what? Experimental value, right? And this one, assuming there was no resonance, no delocalization, so that is calculated based upon the certain data of cyclohexene. So I'll be using that as calculated. So minus 360 plus 208 will be minus 152 kilojoule per mole. You don't have to remember any data, simply understand the concept, that is more important. Hopefully you understood this, all of you. Write this quickly, then we'll proceed further. Is there any doubt to anyone? Done? Can we proceed for the question then, if at all you are done here? Okay. Now I am giving one question. Find resonance energy of 2O in the gaseous form. I am giving you the structure also of N2O. In actual benzene, no. So when they have carried out its hydrogenation, they observed the value to be 208. But without, kind of calculating, without the basis is based upon cyclohexene, right? So if it all consider cyclohexene and then they calculate that, okay, in cyclohexene there is 1 pi bond, in benzene or else that hypothetical compound which they have taken which is having 3 pi bond. So basically it should be minus 360 here, right? So that is calculated based on some data which is you. But in reality something else is there. Now here tell me one thing, this data which is given to you in the question, is it experimental calculated? Is it experimental calculated? Enthalpy of formation data which is given to you, is it experimental or calculated? Experimental. This is experimental. Now which formula you should use for calculating the resonance energy? Yes, good. Manas, Narayan. Which formula we should use? We should use enthalpy of formation for experimental minus enthalpy of formation calculated. Now experimental is given to you, calculated, how will you calculate the enthalpy of formation? Calculated, theoretically, using which data? Using this bond energy data. So please go ahead and calculate the enthalpy of formation of N2O calculated. Okay. So I'll write down the formula here. Resonance energy is standard enthalpy of formation experimental minus standard enthalpy of formation calculated. So calculated means I write down 1 mole of N2O gas is getting formed from its constituent element in the standard state. Half of O2 gas here. So delta H naught for this reaction you have to find out, and this reaction is representing the standard enthalpy of formation of N2O gas, and this one is calculated value. So simply I am writing the expression here. Delta H naught for the reaction will be summation of bond energy of the reactant minus summation of bond energy of the product. And this is bond energy. Reactant you are having N2 means N triple bond N. Plus you are having half of bond energy of O double bond O. In N2O remember N double bond N double bond O is there. So I will be writing bond energy of N double bond N plus bond energy of N double bond O. Please put the values and get the answer for delta H naught reaction. No, Vamsi, some mistake you are doing, beta. Shyam, is that final answer for resonance energy which you are giving me? All of you calculate here. Please place the correct values. Then the correct answer. Here you are having 900 plus you are having 500 by 2 minus this value I think I have given you 400 plus this one is 600. So you are having 1150 minus 1000. You will be left out with 150 kilojoule per mole. So this you have calculated that particular value. So resonance energy will be experimental 80, calculated 50, you will be getting minus 70 kilojoule per mole. Yes. Sai Ganesh also correct. Smriti, somewhere you have gone wrong, beta. Check it out. Some silly mistake you have done. Maybe some values you have swapped here and there. Correct answer. I hope it is done now. So for resonance energy, you will be getting this kind of thing only, right? Now maybe in your module there is one question related to actually benzene, right? So for benzene I am not solving the question, only thing is I am asking certain doubts, you just tell me, right? Because I just want to ask where is the scope of making mistake. I think they have given you heat of dissociation. That value is experimental and you have to calculate the heat of dissociation by using the bond energy data, right? So bond energy data, let us say C, single bond C, CH. Let us say this is X, Y and Z, right? These are the bond energies corresponding to C double bond C, single bond C and CH. Tell me how many C double bond C are there? How many C double bond C? How many C double bond C and how many? Correct. How many single bond? C single bond C, how many are there? For single bond C, how many? 3. CH, do not count it again, okay? This is double bond done. Single bond, then 3 there. CH bond, how many? 6, no? So only scope of mistake is counting in the number of bonds. Otherwise, rest you can easily do. Okay, now we'll proceed towards another small topic here, which is Born-Haber cycle. Now, when it comes to Born-Haber cycle, basically this cycle was developed by the scientists so that they can basically get the value of lattice enthalpy, because it was being difficult to find the lattice enthalpy using experiment. Okay. So they thought, if at all, theoretically by any means, if we can get to know the lattice enthalpy, if at all we are knowing about other enthalpy values by any experiment. Okay. So for that reason, this cycle was developed. Now the next thing is, this cycle is based upon Hess law. So what does Hess law say? Hess law simply states that whether a particular reaction is happening in one step or more than one step, the overall enthalpy change does not change there. It is remaining same. Okay. So now we are going to understand that here. Basically Born-Haber cycle. So this is based on Hess law. Now I am going to write down the enthalpy of formation of this NaCl solid. Now for enthalpy of formation, standard enthalpy, so its constituent elements are sodium and Cl2 gas here. So I'll be writing half of that. So this reaction will correspond to standard enthalpy of formation of NaCl solid. Right? So this reaction is happening in one step. I can make this reaction happen in more than one step. So let us see that. So if at all I am writing this as Na gas, right? So what I have done this, is it representing sublimation over here? So I'll be writing this is delta R H1 naught, which is representing delta H sublimation. Delta H1 naught is standard enthalpy for the first reaction, right? This reaction, this is a general expression. This is the actual name of that process, which is delta H sublimation, right? Now, second thing what we are doing here is we are making Cl gas. So did we break the bond here in Cl2? So I can easily write down this delta R H2 naught is actually bond energy of Cl2 divided by 2. Similarly, if at all I am having sodium gas, it is become Na plus gaseous. So Na gas to Na plus gaseous, will I call this as delta H ionization? Ionization enthalpy, you remember? So I'll be writing this as ionization enthalpy, and I'll be writing this as delta R H3 naught. Similarly, if at all I am writing Cl to Cl minus gas, what is called? Cl to Cl minus gas, what it is called? Yes, electron gain enthalpy. So I'll be writing delta RH4 naught, that is electron gain enthalpy. Now, do you remember, I might have that if I am having 1 mole of ionic compound and if I break it into its constituent gaseous ions, so what energy required or the enthalpy change, that is known as lattice enthalpy, right? So the energy required to break 1 mole of ionic solid into its gaseous ions is basically lattice enthalpy. So energy is required there. Even I can say like this, that if I have to form 1 mole of NaCl solid, that is any ionic compound, from its constituent gaseous ions, so that is also lattice enthalpy, because lattice enthalpy can be defined in both the ways, right? So now am I having these ions here, and these two ions can combine and we can form this, and I'll be writing this as delta RH5 naught equal to lattice enthalpy, and I'll be writing this as negative. We are making the lattice, we are not breaking the lattice this time. So since we are making lattice, right? So the thing is, can I say now here that this standard enthalpy of formation of NaCl is the summation of all these 5 lattice enthalpy. So I can easily write down here that standard enthalpy formation of NaCl solid, that is equal to delta R H1 naught plus delta R H2 naught plus delta R H3 naught plus delta R H4 naught plus delta R H5 naught. So out of these 6 values, examiner may give you 5 values, 6th value you have to find out. Or else, if at all any theoretical question has to be asked, maybe they might give you the entire Born-Haber cycle for any ionic compound, and they may, kind of suppose here I have written delta RH4 naught as electron gain enthalpy. They may not give you this. They may ask you, what is this delta RH4 naught representing? Or else, what is this Na gas to Na plus gas delta RH3 not representing? So either way, a numerical or else something theoretical could be asked, and we have drawn this cycle for NaCl solid, which is one of the very simple ionic compound. You can always draw this cycle for any ionic compound of your choice. Okay? So please write this down, everyone, then we'll proceed further. And this you need not write down this lattice enthalpy, this you already know. Okay, Shyam. Are we done writing it? Okay. Now, the way they have given you in your NCERT is little bit different. So when you read it, you should not, kind of get confused that what I have taught you and what is given in NCERT is different. No. Only thing is the way of representing it is different. I'll tell you that also quickly. You don't have to note it down. What I've shown is the energy level diagram actually. And here they have shown this NaCl solid which is getting formed. So the thing is NaCl solid will be formed from Na solid plus half of Cl2 gas. Now the thing is formation of this NaCl is exothermic. Exothermic means energy will be liberated. So down arrow means energy is getting liberated, right? Now Na solid to Na gas, it is sublimation energy is required. So required means up arrow, okay? Similarly, Na gas to Na plus gas. Again, ionization, for ionizing you require energy. So up arrow for that, okay? Similarly, half Cl2, you are making it to Cl gas, right? So for dissociating the bond, energy required. So up arrow, right? Now after this, they might have shown you something like this, which is actually Cl minus gas plus Na plus gas. Nothing is happening to Na plus, we are simply writing it. We are converting Cl to Cl minus. It is electron gain enthalpy of chlorine, and you might know already that the element with the most negative electron gain enthalpy in the entire periodic table is chlorine. So that means this is down, exothermic process, energy will be liberated. So you are having this. Then after that you are having these two combining to form NaCl solid. So energy is getting liberated. So that is the way, up arrow for energy requirement, down arrow for energy liberation. That is the way they have written the cycle over there. So do not get confused. Okay, do not think that something different has been, kind of taught to you. You should be able to realize the things there. Okay. So having said that, we are done here. Let us move on towards the second law of thermodynamics. Now when it comes to second law of thermodynamics, let us try to understand why even there was a necessity for kind of proposing this law. And for that we will revisit that first law quickly. When it comes to first law of thermodynamics, it always talks about conservation of energy, right? That okay, one form to another form it can change, but the thing is, the amount of the energy is in this universe is going to remain constant. It's not changing, right? Now the thing is, but the first law never talked about why certain phenomena which we observe in nature happen in a particular direction. For example, you might have seen very many natural processes, like water is falling, right? In a waterfall, water always falls from a higher height to a lower height. Have you ever seen water going on its own from a lower height to a higher height, right? Similarly, any natural phenomena you take, like when trees are there, so trees when they grow old and basically they'll be like shedding their leaves and kind of fruits will be dropping down. It doesn't happen. Kind of fruit is kind of getting up from bottom and getting stick to the tree again, or as the leaves are getting again fresh and kind of sticking there. On its own, it never happens. Similarly, gases have the tendency to intermix on their own. Right? That is a natural phenomena. Gases will not start fighting. No, I'm not going to intermix with you. That means that is unnatural process. Naturally, what is the tendency? It occurs in a particular direction. So basically, what is there? Basically, all those natural processes which are seen, there is a particular direction in which they are happening. So scientists thought there should be some property of a system which should change in a particular direction, in a particular way, when a particular natural process is happening. And if at all we are trying to have unnatural process, so it should change according to that. So according to that, they have basically brought one more parameter or one more property of the system, which is known as entropy. So what the second law states? Second law simply states that basically whatever are the natural processes, they are actually irreversible because they are going to get completed in a certain finite amount of time, and they are happening on their own. You are not doing anything there. So all those natural processes, they are happening in a particular direction just because the entropy of the universe is increasing there. So wherever entropy increases, there in that direction, that particular natural process happens, right? And at present, you understand that entropy or randomness, entropy as randomness or disorderliness, right? So that is what is your second law. And you can understand this in a very simple example. Let us take your example. Suppose you are sitting in your study room and you might have made it messy, right? So after, like, maybe you start feeling, no, I need to clean up home. So what do? You clean up your room, tidy it up, take 2 hours, clean it, right? But what after 2 days? The room again starts to become messy. For some people it is 2 days, for some people it is 10 days, for some people it is 20 days, or maybe for some people 2 hours for kind of making the room nice and 1 hour for spoiling it. So what is the natural tendency? To have the things in a messier way, because randomness increases there, right? So that's what is your second law of thermodynamics. Now do not apply this same, no mom I cannot do this, because it is nothing is there in my hand. It is actually second law of thermodynamics. Do not apply that. Otherwise flying saucers will be there. So write down here, for a natural, irreversible, spontaneous process, entropy of the universe always increases. That means delta S universe is greater than 0 for reversible process, and delta S universe is equal to 0 for reversible process. And when I say delta S universe, it is actually delta S system plus delta S surrounding. Write this down, everyone. Hopefully written now. Then for a reversible process, always system and surrounding are going to be in equilibrium. So whatever is the entropy change in the system, exactly opposite entropy change will be happening in the surrounding. So that's why delta system and delta surrounding summation is equal to 0. Got it, everyone? Now I'm writing here entropy, which is S, symbol S is there. Now I'm saying that suppose you are, like, imagine yourself to be sitting in a classroom, right? Offline classroom. Before a teacher enters, there is kind of different in which all of you will be there, right? Now the moment a teacher enters, everyone will be disciplined, they'll be sitting on their benches. So did you enter into another state here, right? So the randomness has reduced or not. So can I say entropy is basically a state function, because through entropy I am able to come to know what is the state in which a system is present. Okay. Now the other thing is, suppose in your house maximum people which can get accommodated is 100. Let us say for a function or something, 100 people at max can kind of get accommodated in your house. So 100 people means, or let us remember 100 will be like as if kind of a wedding hall is there. Let us say 20 members comfortably. Okay. Now what I'm doing, I'm sending 40 members more to your house. So what has happened? The randomness or the disorderliness which is there in your home, will it be disrupted or not? It will be disrupted. That means what? This entropy which is there, is it depending upon the quantity of the matter which is present in that system, because your house is acting like a system now. So can I say that this entropy is an extensive property, right? So simply entropy is a state function and extensive property. So I can write down here, it is a state function, it is a state function and extensive property. Yes? Did you people understand here? Now let us write down the formula here. Mathematically, we are writing ds, small change, is equal to dq reversible upon T. Small change in entropy is this one. For change, you just need to kind of integrate it. So you'll be getting q reversible upon T. Delta S is q reversible upon T. And the unit here is of entropy is joule per Kelvin or else calorie per Kelvin. Please write this down, then we'll understand it. Finished? Please write down done if at all you are done writing there. Done or thumbs up so that I can understand you people have done writing. Are you able to listen to me? Because I'm not able to see any response there. Yes? Okay. Fine. Now let us try to understand very important thing here. Are you able to see that the entropy change is directly varying with the amount of heat which you are, kind of entering into the system or leaving the system, and inversely proportional to temperature. Now, one thing is clear, one thing, let us understand one by one. Suppose you assume that, in a particular, kind of room, that is a closed room, there you have enclosed the gas, right? Now, the thing is, if you, send more amount of heat inside the room, do you agree that basically thermal motion of the molecules will start to increase because their kinetic energy has increased? So did you increase the randomness there? So depending upon whatever, if more amount of heat you are supplying into the system, more entropy change, more randomness, more disorderliness, right? Now what I'm doing next is I'm keeping this heat constant, like fixed value, right? And I'm now talking about two systems. Let us say this is system 1 and here this is system 2. This system is maintained at, let us say, temperature 10 degrees Celsius. This is maintained at, let us say, 100 degrees Celsius, right? So this system means you are having gas enclosed here. Here also you are having gas enclosed. One system is maintained at lower temperature. Another system is maintained at higher temperature. Let us say T1 and T2, right? Now, in both of them, I am sending actually 50 joule of heat. I have fixed this value, right? So the system which I have maintained at lower temperature, their randomness will be less now because less kinetic energy of the molecules, less thermal motion there. Here, system 2, you are having higher temperature. You have maintained the system at higher temperature. So already the molecules are moving with higher kinetic energy, more randomness is there, more thermal motion is there. Now, if I am sending the same amount of heat, that is 50 joule, into these two systems, where you will find more change in the ND, more change in entropy, system 1 or system 2. Good. Sham has given answer. Good. What about others? One. System 1 will be having more impact. So you can compare this system 2, why Smriti, why system 2 beta? It's already having more randomness, right? More randomness, and there you are, kind of sending the same amount of heat, which will be like, it will not appreciate, or else basically you will not have some creative mind is there, ma'am, 5 and 0.5. Arey, we are not calculating anything beta. Okay? Now you understand one thing here. Conceptually you understand. Suppose you are sitting in a quiet library and take quiet library as a system which is maintained at lower temperature, right? Now suppose somebody is sneezing out in the library, suddenly sneezed out. right? So imagine that sneeze phenomena as the mode of transfer of energy there, right? So you suddenly it is a quiet thing. So what will happen? You'll get more distracted, more disruptive. Suddenly randomness will be created there, right? So their entropy changes more. Okay. Now suppose you are walking on a busy street, crowded street, where already there is so much of randomness already there, right? And if in that crowded, busy street, if somebody sneezes, there will be entropy change, lesser amount, right? You won't even notice it. Are you able to understand? So the system which is present at lower temperature, so impact of kind of supplying the heat to that will have more entropy change. So understand that carefully. I hope it is clear to all of you. Now let us go for the next one here. Calculation of delta S for an ideal gas undergoing a process. So the thing is here, undergoing a process means the system is changing the state from one state to another state. So it can also do by reversible path, it can also do by irreversible path. Whatever is the path followed by it, delta system is not going to change here. Why delta system is not going to change here? Correct. Because S is a state function. Now I am writing two general formulas which we are going to modify according to the processes we are going to see. So all of you must write down those general formula. So delta system, that is equal to NCV ln T2 by T1 plus NR ln V2 by V1. Similarly, delta system equal to NCP ln T2 by T1 plus N ln P1 upon P2. So write down these two general formulas. After that, we are going to modify now? Is it audible now? Yes. Now I was talking about isothermal process. Yes, some technical glitch, need not worry, right? Now, when we are talking about isothermal process, you can carry out reversibly and irreversibly. We are first going to derive, just going to derive the expression, okay? Now for reversible, I am just taking one of the expression, which is delta system NCV ln T2 by T1 plus SNR ln V2 by V1. And remember, whatever formula I have written here, it is simple to remember also, because if CV is coming, volume term should come V2 by V1. If CP we are writing, pressure term should come. And the thing is, pressure and volume, they are inversely proportional to each other. So volume we have written V2 by V1, so the pressure should be P1 by P2. Are we able to understand that? Right? Now, here basically, if temperature is same, so this value will be vanishing, it will become 0. So ultimately, will I be having delta system, which is equal to NR ln V2 by V1. And similarly, if at all I go on the other equation, this also T2 by T1 will become what? Ln of this will become 0. So I'll be having NR ln P1 by P2. So I can write down this as NR ln P1 by P2. So simply remember the formula here, which is simple. Now, when it comes to surrounding, and we are dealing with the reversible process, and I've already told you for a reversible process, delta S universe is 0, right? So I'm going to write down here, for a reversible process, delta S universe is equal to 0, which implies delta system plus delta surrounding, that is equal to 0. That means I'll be writing delta S something which is equal to minus of delta system. So formula will be the same thing, only thing is put minus sign over there. Okay. So I'm going to write this down here. So delta S surrounding is minus NR ln V2 by V1 or minus NR ln P1 by P2. And majority of the time, options will also be given in terms of ln only. Need not worry. If they give you an expanded form, expanded in the sense log to the base of 10 form, so you can always convert this, right? But normally for entropy, if they're asking you, they can give you question also in this format only. They'll give you 2 moles, 3 moles, whatever, and the pressure value is 20, 10. So easily you can write down. Suppose 3 moles is given. So minus 3 R ln of 30 upon 10 is 3, ln 3. Getting it? Please write this down, then we'll proceed further. Now let us move on to the next one, which is irreversible isothermal process. Now, are you able to recall that I said that it is reversible or irreversible? Your delta S system is not going to get impacted, right? So the thing is, delta S system formula remains the same. So delta S system will be NR ln V2 by V1, and that is equal to NR ln P1 upon P2. Only thing is, delta S surrounding is going to change here. Now, are you able to recall that we have written delta S formula as Q by T? Now, since I am writing delta S for the surrounding, so the parameters for the surrounding should be written. That means I should be writing Q surrounding upon T, right? Now, temperature of system and surrounding is same, a uniform temperature. That's the reason I have written T here. Now, do you understand that whenever we are performing an experiment, so system will be small, right? And surrounding will be like, huge. So whenever something is too huge, it's become very difficult to measure the parameters accurately. So scientists thought, if the surrounding is too huge, we cannot measure the parameters of surrounding very accurately. Why not try to express surrounding itself in terms of system? Because system is small, we can measure the parameters of it more accurately. So I can write down here this as minus Q system upon T. Now what for I have written minus? Because the thing is, whatever surrounding is gaining, system would have lost, no? So that's the reason minus. Now next thing is, do we know from first law of thermodynamics that delta U is equal to Q plus W, and for an isothermal process delta U is going to be 0, so that means Q will be equal to minus W. So I'll be placing this W here, that is minus of minus W system upon T, and this makes it as work of the system divided by T, W system upon T. Now, do you remember what is the formula for the calculation of work done in irreversible isothermal process? Does anybody remember the formula? Work done in an irreversible process, in isothermal process. Nobody remembers, huh? Yes, correct. Smriti has written that will be minus P external delta V. So I am writing V2 minus V1 upon T. Do not think that you have to remember so many formula. Where I am putting a tick mark, you have to remember that only, right? Now, the thing is, do you remember I have given you one more alternate formula? I think, who is there? Rajni has already given the alternate formula, which is minus nRT 1 minus P2 by P1. So I'll be writing the alternate formula minus nRT 1 minus P2 upon P1, and temperature is already here. This will get cancelled. So I'll be having minus nR 1 minus P2 by P1. So this is the formula which you have to remember. Only these two formula. Do not worry about it. The thing is, I am telling you the derivation because how it has come, so that you should have understanding of it. And the next thing is, we are going to just tabulate all those formulas so that when you are revising, you just have to revise those formulas itself. Are we getting it? Quickly finish writing it, then we'll proceed for the tabular form. Yes, are we done writing? So I am simply making a table now here. So where we are going to write down reversible and irreversible. And then you are going to write down delta system, delta surrounding. And this table is only going to be important. Reversible means nR ln V2 by V1 or else nR ln P1 by P2. Delta system does not change for irreversible process. So I'll be writing nR ln V2 by V1 or else nR ln P1 by P2. We are simply enlisting them. For a reversible process, delta surrounding is minus of it. So minus nR ln V2 by V1 or else minus nR ln P1 by P2. And here it is going to be minus P external V2 minus V1 upon T or else minus nR, and you are having 1 minus P2 upon P1. Do remember the formula, that is most important here. Right? So do memorize the formula before coming for the next class. Okay. So today we'll wind up here only. Hopefully you people understood this. Right? So keep learning and keep enjoying the things here. Thank you. Yes, I'll share the QR code for those people. Yes, QR code I remember. As such, I will send kind of pick of that QR code so that you can scan it.